morning engineering 2. Woo. Okay, so let's talk about the fits. Let me see if I have the table open. So the fits. We have talked about clearance fits. We have talked about interference fit. We have talked about transition fits. And we have done it graphically. I believe that's my preferred way. You can also do it mathematically, but I usually like the graphic approach because I don't have to remember anything. I just gotta look and sketch and see what I need. You can also use, if you want to determine the fit, you can also see this. Calculate the biggest shaft, calculate the smallest hole, and then ask yourself, will the biggest shaft fit into the smallest hole? If it's yes, you have a clearance. If it's not, you might have to calculate the smallest shaft and the biggest hole. And then you will ask yourself, will the smallest shaft will fit into the biggest hole? If yes, you have a transition fit. If no, you have an interference fit. Right? That's another way of doing it. If you guys recall correctly, if you guys remember, we have done the shaft base sketches. I've done it a little bit different, but you can do it like this, right? So this guy is what we have done, right? I just put this shaft on the outside instead of putting it here. This guy put the shaft inside of the hole, and I also have the interference, right? When my shaft is bigger than my hole, and I also have. Oops, I don't want to move that one. Let me flatten it. So it doesn't move. Oops, I don't like that one. I actually want the names. Let's one more time. Let me put it on the top so it doesn't disappear. Flatten it. Let's try it. There we go. What you guys have done, or what I have done in the lecture, I have used the shaft as my reference. You guys remember what I did? I just made an imaginary line right below the shaft, right? And then I put the shaft and the hole both in the same place. And at that point of time, I just went and say, hey, let's take a look at the tolerance zones and see if my shaft is going to fit in the hole. And we look at the tolerances, and then we created different sketches. In fact, that is your cheat sheet. Different sketches, one for clearance, one for interference, and somewhere one for transition. You can do a similar approach, but now instead of you messing from the shaft, you can also mess with the hole. So you guys will notice here I have a huge hole. Let's see a huge hole. That's the huge hole. That's the bottom of the huge hole, right there. This one is the biggest the hole I can get. This guy represents the smallest the hole I can get, right? And again, you grab the shaft and you start putting it inside of the hole. This is what they call it, the hole-based system. You can use the shaft as your reference. You can use the hole as your reference. In fact, I believe, don't quote me on this, the tables that are given to you are based on the hole-based system. When you make a huge hole, you make a bunch of shafts and you put them inside of it. Now, what would be the difference between both of them? Pretty much none. I mean, yes and no. I guess the way you organize the table, right? You say, okay, I want to say on the hole basis system, everything will be based on the hole or on the shaft. But in terms of tolerances, though, it will be the same. Okay, so for example here, I have the shaft tolerance zone and the hole tolerance zone. What is this? This one is clearance, right? Your tolerance zone on the hole is above the shaft, right? Which means you have a clearance condition. This one over here is a transition fit. I'm overlapping the tolerance zones. And this one over here, it is my interference tolerance zone. And again, if I were to come over here and look not at the shaft basis but at the hole basis, this over here, again, it's the same. It's a clearance, a transition, and an interference line. It just depends on what you want to use as your reference. I usually love to do my shaft and my hole separate. You guys will notice that these guys like to make a big hole and put a bunch of shafts inside of it. Or you can make a big shaft, and then put the holes inside of the shaft. You can call it either way. Right. Now, let's take a look at the tables that are given to us, right? You will use the tables directly if you want to determine the fits between, let's call it, determine the way the things are going to match within new to new parts. And you can also adjust it slightly to determine the fits for existing parts. We'll talk about what about if I have an existing condition? How would I do it? Okay, how does the designer choose the correct tolerances to fit the missing parts? Well, there are standard fit tables that can be used, which provide the tolerance rules for different size parts so that they're given a standard fit. The parts will behave a similar fashion. So somebody did the math and did a bunch of math with a bunch of tolerance zones, with a bunch of allowances, tightest fits, also with a bunch of clearances, the loosest fit, and he came up with a huge amount of tables. And he said, you know what? I am going to describe what happened when I when I have a clearance fit, right? So I don't know when you remember I have this guy. So they did something like this. Let me show you. Let me see if my camera works. So they did something like this. Just like this but bigger, okay? They determined they went in the machine 3 million holes, 3 million shafts with different tolerances each, different allowances each, and then they went doesn't fit, doesn't fit, it fits, doesn't fit, doesn't fit, and came up with a bunch of flavors to say. We call them the standard fits. The flavors that will behave based on somebody else that they already did it. And since they don't want to redo this exercise, they can come up with these tables and they call it standard, which means everybody should use them if you don't know how things are going to behave, so you don't have to go through the same process. So let's take a look at the flavors. This is what we call it, the flavors of the fits, the fittest. Let's see if I can come over here and subdivide my flavors. I'm going to call that flavor number 1. And I am going to call this guy flavor number 2. Right? And the one in the middle, I'm going to call it flavor number 3. Okay? So this is how they did it, okay? Let's say, you know what? I'm going to call the sliding fits, running sliding fits, are things that have a lot of wiggle room. Let's call it wiggle room. Lots of wiggle. Lots of wiggle room. Let me see if I can make this guy big. And then right after I told you about the wiggle room, we're going to start looking at some of these things. Okay? And we're going to put this guy, and I'm going to call it lots of wiggle room, which will be my running sliding fit, right? Things that are like wiggling. Then he said, you know what? I am going to start now locating. And since I'm going to have locating parts, I'm going to take away a little bit of that wiggle room. So I'm going to take away wiggle room, and we're going to call it clearance locational fits. So let's call it less wiggle, less tolerance, right? So my tolerance, because remember the tolerance will allow for the shaft to go too big or too small. If I take the tolerance away, that means my fits are going to be more closely precise because there will be less variation on the size of the shaft. So less tolerance, less allowance, less gap in between them. Less wiggle, less tolerance, less allowance. And then they say, you know what about if I want to not have any wiggle, no wiggle at all, or if I get to have a wiggle, I'm going to have a wiggle really small, and then allow for the materials to fit together, but make it a little bit hard for me to disassemble. Right? I'm still going to be able to disassemble without damaging the part, but it won't be clearance anymore. Things are not going to have wiggle. In fact, let's call it no wiggle. I'm going to copy the note over here, and I'm going to call it the no wiggle zone. Oh, pretty little wiggle. Let's call it pretty, I think I call it pretty little wiggle room. And again, I will still have less tolerance, way less tolerance, right? So now I'm messing with things. And again, in this case, I'm actually going to have an interference in the clearance condition. You guys remember that this is the transition. We call it the push fit. When you can put it inside, it's a little bit hard to put inside, and it's a little bit hard to put out. Push fit. And they say, okay, so now that will be the one. That will be the one with pretty little wiggle. Let's do one without wiggle. And they did two without wiggle. They call this guy the interference locational fits. And then this guy will not have no wiggle. See, no wiggle. No wiggle. Because it's interfering, right? No wiggle at all. In fact, the things are going to start interfering with each other. And then he will, you know what about if I want to have things that are going to be so hard that the only way that I can match them is by messing with temperatures. This guy is the force or shrink fit. I need to force it and I need to increase the temperature to account for shrinkage. Once it solidifies, once it has cooled off, the expansion will come back and will keep the thing fused together. So this guy is no wiggle and need to mess with temperature and force. Okay. So by the way, the other one before, we need to mess with force, but not necessarily with temperature. No, with force. All right. So somebody came with the flavors, and he come up RC fits, LC fits, LT fits, LN fits. The easy way to remember which ones are there. You just remember that the C's stands for clearance, and the T's stands for transition, and the rest ones are interference. Right? Okay. So let's take a look at some of these flavors. I think I'm just gonna cover the RC flavors and then we will glance through the other flavors, but they're all same concept. Okay? Let's look at the RC flavors and let me see if I can show you a table. Okay, so this is the RC flavors. So you have a size 0 to 0.12 inches, 0.12 to 0.24. What is that? That's the diameters. So just like before, I have a pin and I have a hole and I have drawn it 1 inch. And I want to ensure that I know how to use the table. I look at the table and say, okay, what is my 1 inch shaft? Oh, it's over here. That is my 1 inch shaft. That's where it falls. 1 inch shaft, 1 inch pin. Okay, how do you want it to mate? Well, if I wanted to mate it, I want to see flavors. Let's take a look at the flavors. Flavor number 1, RC1, RC2, RC3, RC4. You get all the way to the RC9. And remember, the RC stands for clearance. In fact, we call it the running or sliding fits. So RC1 stands for the closest sliding fits for accurate locating parts that must fit together without any play. So a sliding fit that doesn't have too much wiggle room. RC2, it is used for sliding fits where accurate location is important but the greater maximum clearance. So a little bit more wiggle room. RC3, it is used for precision running fits. This class ensures that the closest possible fit that can be expected to run freely. A little bit more wiggle room. RC4 is used for close running fits and accurate machinery with medium surface fits and pressure when accurate locations and very little play is desired. More wiggle room. Continue with more wiggle room. I will see RC5 are used for medium running fits on accurate machinery with higher running speeds and heavier pressures. RC7 is used for free running fits that accuracy is less important. More wiggle room. And where the significant temperature variations are likely, if things are going to expand and they're going to be moving, they need to have a lot of wiggle. Classes RC8 and RC9 are used for loose running fits when large tolerances are necessary together with an allowance on the external parts. Much running. Now let's take a look at the chart, right? I give you guys a cheat sheet. You should have this in your handout. And the way I like to look at the RC fits is by looking at shaft and looking at the chart. Right? And remember, somebody already did this. Somebody got a bunch of holes and a bunch of shafts. And then you just look at the tolerance zone, right? This is the hole in the shaft. And again, you hear the hole and the shaft. They overlay both of them, one on top of each other, and it looks like this. Hole and shaft, hole and shaft, hole and shaft. Remember, the hole is above it, so that means I have a clearance fee. And then you guys will notice that the RC1, smaller tolerance, less allowance, less tolerance from both of them. So the more restrictive clearance fit is RC1. And as I go from RC1 all the way to RC9, you guys will notice that I start messing up with the tolerance and the allowance. I start separating these guys. So a lot of wiggle room, a little less wiggle room, less wiggle room. We call these the flavors or the clearance sliding fits. How do you choose the sliding fits? Well, you can do it 2 ways. You can come over here and try to come up and follow the descriptions of this. and try to come up with a sweet spot by just the text per se, just understanding the tolerance and understanding the allowance. Or you can also ask your boss. Or maybe you do it by experience, right? Maybe what you do is you try one up and then you go through the prototype process. And the prototype process will put a thing together in terms of assembly that you can actually test and say, yes, that's what I want. It's another way of doing it, right? Or ask your boss. Maybe your boss will have pretty good insights. So you know what? This guy is going to be subjected to temperature. There's going to be a higher moving load. I think based on my high experience, that's what you should use. Okay. Now, how do you read this one? So, previously told you, step number 1 is look at your shaft. Step number 2 is look at your flavor. Once you find your flavor, let's say that I choose RC4. And let's say that I did my shaft slightly bigger here. Let's say I did it 1 1/4, right? So you look at your shaft in the range where you're looking, then you choose your flavor, right? Grab your shaft, move it across, and then you will get some numbers. What are those numbers? Well, those numbers are are pretty much what you're going to use to determine your fits in your calculations. But what you can do, I mean, you can also literally just grab it. Let me take a look at one. Let's say, I just want to make up an example. Let's say that within this range, I have a 1 1/4. I have a 1 1/4 shaft, okay? Now, these tables are given to you, and it tells you somewhere on the bottom, they're given to you at 1/10,000 of an inch, or 0.001. So, for example, the way you would read it, let's say that I started with my nominal size of my shaft in a hole somewhere over here, right? And again, I know. Sorry about this. Let me grab the other camera. Let me draw it. Makes sense, right? Step number 1, you will grab and you will say, okay, so I have a shaft. Let me get a pen. You will go and you say, okay, so I have a shaft, looks like this, and I know that I'm going to have a clearance fit. I look at my flavor, and I know it's going to look like this, right? I look at my flavor, and my flavor in this case, what was the flavor? I don't remember the flavor. Let's see if I can grab this guy and put it on the side, and I'm going to just write it. 1.0, 3.6, plus 1.6, 0, negative 1.0, and 2.0. Keep in mind that you also want to look at the table, right, on the top, because one of them is going to be for the hole, and the other one is going to be for the shaft, and they also want to tell you your clearance limits. See, clearance limits for flavor RC4. Okay, remember you got flavors. So here I just wrote it. I got in those numbers and I wrote them down. Now, how do you work on this? How do you use them? Step number 1, you graph, choose your range or your shaft, which in my case, I said that my shaft was going to be 1 1/4, okay? Which is the diameter, right? The diameter 1 1/4. And then the values that are given to you in these 3 little slots are to the tau, 0.001. So we have to translate this into tau. How do you translate it into tau? Thousandths of an inch. You can rewrite it on the side if you want. So you can do it separate. These are the clearance limits. This is the hole. This is the shaft. And let me move my paper slightly to the side. You grab those numbers, and what you do is you copy them, but don't put the 0, the dot, right? You write the 1 and the 0, and whatever the dot is, which in this case is right here, you're gonna scoot it over 3 times to the left. Okay, so 1, 2, 3. That's where the dot's gonna be. 0, 0. And let's do the other one. Let's do the 3.6. So again, I just put the 3 and the 6, right? And then I scoot it over from wherever the dot is, which in this case is right there. 1, 2, 3. And that's where the point is going to be, 0, 0. In other words, this is 3.6 tau, 1 tau, 1.6 tau, negative 1 tau, negative 2 tau. So let me write them all. And again, I want to say 1, 6. I'm going to grab, and I'm going to put 2 extra zeros because I went 1, 2, 3. That's where the point is. And then the 0, I don't have anything. I just put 0, 0, 0. And then for the 1, I wrote the numbers, and then I go 1, 2, 3. Right? That's where the zeros will go. And then for the 2.0, I just write the 2 and the 0. 1, 2, 3.00. Right? 3.6 tau, 3.6 thousandths of an inch. 1,000 of an inch, 1.6 thousandths of an inch. And we don't call it thousandths of an inch. We probably should. Well, we just call it thou. 1 thou, 1.6 thou, negative 1 thou, 2 thou, 3.6 thou. In reality, this is what is the equivalent, right? Thousandths of an inch. Now, what do I do with this? After I know that my values are actually given to me in thous. You go and you do a little bit of math. Not too much math, it's a little bit of math. And remember, they gave it to you for what you're gonna do to the hole and whatever you're gonna do to the shaft. So let's say I wanna determine what is gonna be my shaft. So what is gonna be my shaft? So you got 1.25, and by the way, this guy has a minus. Don't forget the minus. And if it has a plus, don't forget the plus. And the other one should probably be a, I don't know, let's go see what it's a minus or a plus. So it's a minus. Don't forget the minus, okay? Because then your math will not work. Don't do it like me. Don't forget. Step number 2, after you do the math and you don't forget the minus, then you literally just do the math with that. So it's 1.25 minus 0.001, 1.25 minus 0.002. And you put it in your calculator. 1.25 minus 0.001 will give me 1.249. Minus 0.002 will give me 1.248. Now, what do I do with these numbers? That's my shaft, I already got it. I just gotta put it over here. So the smallest that I'm gonna use is gonna be 1.248, and the biggest that I'm gonna do will be 1.249. 1.249. Okay, and I can do also the same concept for the hole. Okay, so what is the hole? That's my question, right? What is my hole? Well, you started with 1.25. You look at what happened to the hole, and you do to it. Okay, so this guy, that means that's 0.0016 plus 0.0000, right? There's nothing that I'm doing, which will mean that my shaft will be 1.2516, 1.2500. So again, what do I do with those numbers? That's it, I'm done. Now you just gotta write them down. 1.2500, 1.2516. That's how you work it, right? So you go and you say, okay, so I want to find, I have a shaft that is 1.25, and I need to fit a shaft to a hole. I know that I started with 1.25. I go to my tables and I look the range of it, and then I also look for the flavor. They say that I want a flavor RC4 in this case. I copy those numbers, okay? And remember that those numbers that are given to you, they are given to you in thous. That means I gotta scoot over the decimal place 3 times to the left. So this is my thou version. What do I do with my thou versions? I just say, okay, so if I start at 1.25, I gotta do whatever the table told me to do. So 1.5 minus 0.001, right there. It gives me the answer. It gives me the answer. I grab the values that I calculated, and that's gonna be my shaft. I do the same thing with my hole. Whatever values I got in from here, I do to my hole, and I put it right there. Boom. Okay, and then you guys will wonder, Professor, they give me an extra column. What is that column for, Professor? Well, that column, it is your minimum and your maximum clearance. Let's take a look at it. Okay, so how would I do it if I want to actually calculate it? Let me go get a pencil here. Remember, my minimum clearance is when my shaft is the biggest and my hole is the smallest, which in this case is 1.2500 minus 1.249, right? Which is 0.001. And my that's my tightest fit, right? My loosest fit, my maximum clearance, minimum clearance, maximum clearance will be 1.25, 1.256. It's right there. 1.2516. This guy minus that guy. 1.248. Boom. Which is point so 3.6, 1, 2, 3, 0.00. 0.0036. So if you were to grab this guy minus that guy, we'll get this guy. 0.0036. So what is this? Remember, the values that they gave to you, they gave to you in thous. So you will have to scoot them over So you can get these values. So when they give you the clearance limit, exactly that's what they're giving you. They're giving you the minimum clearance and the maximum clearance. That's how you use it. Somebody, let me do a recap. Okay, recap. A little recap of so many numbers. Let me see if I can get back this. There we go. Let's do the recap. Somebody made a bunch of flavors, and they call it RC fit, LC fit, LN fits, FN fits, LT fits, for clearances, for transitional fits, and for interference fits, where they mess up with the tolerance and they mess up with the allowance. And then they put them in the big old tables and they try to describe them. And once that they describe them, they say, okay, if you want to go that way, use the flavor that I gave you, right? And the way they give it to you, they give it to you in thousands. So you have to make them into real, right? Which thousandths of an inch is 0.001, right? So you divide everything by 1,000, which is this. You screw over the decimal 3 times. And then you grab those ones and you apply them to whatever your design size is. In my case, I imagine that I had a shaft that was 1 1/4. And then I did the math, right? And then all the numbers that they give it to me, they are pretty much telling you about my limits, right? Minimum clearance and maximum clearance. When you call it out on the drawing, though, you're not going to call it out like this. For your shaft, I mean, that's where your tolerance come about, right? You would call them like this. You can do direct limit, which that's the one that I like to do, right? And if you were to have a hole, don't forget, it's a diameter, in my case, right? And in terms of the hole, you will call it out like this, right? 1.2500, 1.2516 diameter. Boom. Now you have the size, upper and lower limit that will behave exactly the way you want it to behave. Now, let's take a look at your homework. By the way, you have more RC fits, you got LM fits, you have interference fits. And again, we want to talk about metric fits because those ones are reserved for another class. We do metric drawings when we do the ETEC 34, which is the advanced course for this. Let's take a look at your cheat sheet and then we'll take a look at your homework. Okay, so you guys will notice that the cheat sheet that I gave you, especially this one, is showing you the tolerance zones. And again, you go and you flip them, and they're telling you the flavors. The RCs are here. The LCs is still clearance, right? And again, because I started moving away from here, and RC will be the most restrictive, I had to zoom in after that, right? And this is why we call it the zoom in, make it so much zoom in. Continue zooming in, right? Decreasing the allowance, decreasing the tolerance, all the way till I get to the transition. And then after I get to the transition, I start overlapping my tolerance zones. I also have a flavor of them. And then right after that, then I start interfering things. Locational interference, all the way till I get to force shrink fits. Things that won't be able to be assembled unless I mess with the temperature. And you guys will notice you have this FN, the shaft tolerance zone way above the whole tolerance zone. Because things will not fit unless I change the temperature. And you also have flavors of them. Let's stop the recording. And this is